Howdy, my name is Weiss Stanley, and this is my historical engineering presentation for the 2024 Should I Be an Engineer LeTourneau dual credit class. Starting off during the classical antiquity period, I'd like to point out how water wheels changed throughout the years. Water made for some great sources of energy. It's already there, it's already moving in streams and rivers, people just need to find a way to harness it. Now, initially, water wheels spun horizontally around an axis. This worked, but it was very inefficient. When wheel designs were shifted to a vertical axis, efficiency improved greatly. Harnessing channels and aqueducts, you could reach up to 90% efficiency since gravity could be properly utilized. The timeline for the water wheel is incredibly wide in scope, with the first records being described in 3rd century BC in China, Rome, and Egypt. These were used for several applications, primarily for milling grains, but also to drive hammers for blacksmithing and pumps for irrigation and drainage control. The water wheel saw practical usage and improvement all the way through the Industrial Revolution, and eventually led to its replacement, the water turbine, which is still used to generate electricity today. Its usage primarily involved the mechanical field, but impacted the civil field as time went on. It's hard to point out an exact cost for this since the scope is so wide, but I find it interesting since the water wheel was used so widespread and for so long to access a relatively simple form of energy. Next up, I'd like to talk about the invention of the mechanical clock. People have been keeping track of time for as long as time has been around. Originally, this was through sunrise, sunset, and seasons. Later on, more cultures began to introduce calendars, sundials, and water clocks to break up these cycles into definable series. However, as time progressed, a more granular, quantifiable way of time measurement was required. The Catholic Church actually played a large part in the invention of the clock due to their strict observed prayer times. As such, the first recorded weight-driven mechanical clock was installed in England's Dunstable Priory in 1283. The industry grew fairly quickly with growing demand for improved timekeeping. Early clocks were very inaccurate, however, often losing several minutes a day. However, as time went on, they grew more reliable and widespread, eventually being in every church and town square. By the 15th century, clocks began seeing domestic use and were able to be put into a portable form factor, changing the energy source from weight to a coiled spring. Now, a book which I highly recommend called Longitude by Dava Sobel accounted for the widespread mission to find a reliable way to track longitude at sea, which could be accomplished with a reliable clock that would withstand the movement of the ocean, which was later invented by John Harrison. It's a great book, definitely worth reading. I find it interesting how many roadblocks the mechanical clock faced in its development and the effort for ever-increasing accuracy. This innovation primarily had to do with the mechanical field of engineering. It's hard to pinpoint the exact price of these first clocks, but for reference, they were equivalent to today's cutting-edge, state-of-the-art supercomputers, so they certainly weren't cheap. Next up is the scientific revolution period. Now, one of my favorite pieces of trivia is that the submarine was invented before the bicycle. As crazy as it sounds, it's true. Diving bells had been experimented with before, but the first recorded use of a submarine, as we know it, was in a writing by British mathematician and naval expert William Bourne in 1578. Around the 1620s, the Dutchman Cornelius Drebbel created the first submarine as we know it. Now, don't get your hopes up. This was basically a waterproof barrel that could be rowed underwater, with hand vices controlling the volume and depth. However, this could be operated at depths of up to 15 feet, which was enough to wow the public and is still impressive given the time period. Thanks to innovation during the scientific period, it's said that experimental barometers were used to measure depth, and saltpeter was used to allow for longer air supply underwater. It didn't take long to realize the warfare potential of the submarine. The first offensive submarine was used during the Revolutionary War, called the Turtle. The idea was to drill a hole in the bottom of a ship and place an explosive charge. However, the hole proved to be too strong, and it didn't end up working as planned. The invention of the submarine was primarily mechanical, with usage being enabled by chemical innovation. Obviously, it went on to have tremendous effects in the field of war engineering. Moving on to the first Industrial Revolution, in the early 1800s, the town of Chicago was ridden with diseases due to its unsanitary conditions and poor drainage. Waste, both civil and industrial, was thrown into the streets and into the river, draining to Lake Michigan, which happened to be the town's water supply. In 1855, the city called upon engineer Ellis Chesbrough, who previously designed a water supply system for Boston, to create the first comprehensive sewer system in America. Now, since Chicago was not built at all with this in mind, the whole city had to be moved to accommodate a new sewer system. Buildings were jacked and raised to allow space underneath, sometimes up to 14 feet. and pipes were built on roads and then covered up to create new roads. Now, the scope of this is just crazy to me. The whole city was literally raised up and moved to allow for new infrastructure to be built. Now, this is arguably one of the most interesting stories of civil engineering to me. I highly recommend a book called How We Got to Now by Stephen Johnson, which has a chapter covering this, and it goes a little more into depth. There's no comprehensive cost list for this whole project, but we do have one reference. A contract for raising one of these city blocks cost about $350,000, which is about $11 million in today's money. Now, expand that to a whole city. It was no small ordeal. During the second industrial revolution, the economy slowly began to globalize. Products were being shipped across land and sea at an increasing pace. However, since this development was so new, it was very disorganized. Goods were shipped in individual boxes and barrels, making it hard to load, unload, transport, and secure, and making it more vulnerable to thieves. Malcolm McLean, the owner of a trucking company, saw these issues and came up with a better solution. Large cargo containers were used for military purposes, but McLean saw that the current design needed vast improvement. In 1956, he sold his trucking company, teamed up with a local engineer, and designed the first ISO container, a durable, modular, and most importantly, standardized shipping container that could be easily moved, sealed, and loaded. The container allowed for more efficient shipping, safer shipping, and smaller workforces. All containers come in a standard width and height with varying standard lengths. The same container could be loaded onto a boat, then onto a truck, then onto a train in a fraction of the time that it would take to load the individual products. It fascinates me that this relatively simple idea completely overhauled the shipping industry and arguably the entire economy as a whole. It's had major implications in the civil engineering field since ports, factories, and railroads were all accommodated to work with this system. It's also had effects in the military field since the U.S. turns to McLean during the Vietnam War to use his containers. A standard 20-foot container costs about $2,000 to build, but cuts down on shipping costs massively. Now, in the age of information, I'd like to finish up with arguably the most influential development of the modern age, if not all time: modern semiconductor manufacturing. Every single industry has been affected by modern computing. Everyone talks about how computers used to be the size of a closet and now can fit in the hand, but modern semiconductor manufacturing is the process that makes this possible. A semiconductor, by definition, is a material that can behave both as an electrical conductor and an insulator depending on the conditions it's exposed to, which is essential in transistors and integrated circuits. A single transistor started out the size of a light bulb, but now hundreds of billions of transistors overlapped in a complex array can fit in the palm of your hand. This is done through an incredibly complex process. Since we don't have machines small or precise enough to build the microscopic maze of a modern computer chip, the whole process is done chemically. Now, this blew my mind when I first learned about it. First, a silicon wafer is prepared, which has to be perfectly clean and smooth down to an atomic level. Next, a high-powered laser etches a precise pattern onto the disk, revealing tiny bits of exposed silicon. Now, you go and put it in a plasma shower, which goes and eats away at the material, then builds it back up and creates tiny little imperfection. Then it eats away, builds it back up, tiny little imperfection. It repeats, till eventually you end up with a whole complex sandwich circuit of conductive trails. Now, these behave differently depending on what temperature or electricity they're exposed to. Sometimes these trails can be as little as 4 atoms apart. It's crazy. These disks are, divided and packaged up at that point. But how did we even begin to find this out, let alone do it? It's just crazy to me. Now, the semiconductor industry is worth billions and billions of dollars, with hundreds of millions of dollars being put into research for a single chip, and semiconductor labs costing $10 to $20 billion to build. Once a 12-inch silicon disk is etched, it can be worth anywhere from $5,000 to $10,000. And this affects all fields of engineering, but the development in and of itself is electrical and chemical. I became interested in this topic after I was invited to visit a university semiconductor lab with a friend who is in the industry. Now that sums up my presentation. Like I said, I find these examples of engineering incredibly interesting and important, and it's so interesting to see their historical context. There are so many more things I wish I could cover, but these are my favorites for the given time periods. Thank you for watching, and God bless.